Okay, everybody, let's take a look at these Week 1 Science ACT Prep questions. The first question they start out with is really just telling if you know how to look at a graph or not, and read those. So they give you 4 different graphs. All of them have to do with death. So this is all-cause mortality, homicides, accidents, and things like infectious disease. You need to understand there is an X and a Y axis. The X axis has age. Y-axis has rate of death or mortality, death per 100,000. And so that's really just the rate that they die. They also have a little key because there's 2 lines on each one, and they point out that the hollow dots are the men and the filled-in dots are the women. Now, if you look at your question, it's the probability that a man in his 40s will die in an accident is about. Well, probability is a little bit of a trick because it really is just looking for the rate or the ratio that they're going to die. So we have a man. We know we're going to look for the hollow dots. It's in his 40. We're going to be able to go to 40. And accident narrows it down to this little square here. So we're going to look at this one. We're going to go over to 40. Go straight up until we hit the line that has the men in it, and then we just draw a line straight over to see the rate, and that means there's 10 right here for every 100,000. Now that's a bit of a problem when we look at the answers because look, they're all in 1 in so many millions, thousands, things like that. So that's okay because we can reduce these. So we just remove a 0 from both ends, and we have 1 over every 10,000, and those are equal. Those are equivalent ratios, and so 1 in 10,000 is our answer. Answer B. Number 2 is looking at graphs as well. It just tries to trick you a little bit because it puts a secondary part of the graph. It has a pop-out part that gives you a whole lot of more information. It lists all these different household appliances, but your main bar graph here is just the cost, your energy cost or cost of electricity broken down per month. If you look over here at your question, it wants the total cost of electricity or energy for the month of February. So you only need this one, and we're just going to go over until we find February, go to the top of its bar and draw a line over to the y-axis, which is the cost, and it's right under 120. It's well over 100, but not quite at 120. So if we look at our answers, 100 is too little, 132 is too high, so the only one it could be is $116, and that becomes our choice, answer B. All right, by 3 it gets a little bit trickier because it makes you read a whole bunch, but the gist of it is there's 2 scientists. They're arguing about putting manganese, I think it is, in fuel as an additive to make get better gas mileage in cars. Number 1 is for doing that. Number 2 is not. You can read them. They're fine arguments. But then we need to know what we're actually looking for in here. So I like to read the question. New experiments could discredit the position of scientist 2 if they were to show that. So basically, what evidence here would discredit only scientist 2? So we're only really concerned with scientist 2. So you need to understand his point of view. And his overarching point is that we're not sure about manganese being in the air because it might go directly to the brain. But we can look at the evidence they provide. So even large amounts of manganese in the blood do not damage the body, basically. Okay? So if they don't damage the body in the blood, is that his point? Well, he admits that it doesn't in the blood. He says, while it is true that manganese is in the blood, it is rapidly detoxified by the liver. Okay? So he's not worried about that. That wouldn't discredit him at all. Letter B. Air ordinarily contains small amounts of manganese. Well, if you read down here, he says, while airborne manganese has not been shown to pose any danger. That means he's already aware there already is a small amount of manganese in the air. We have that naturally. He's a scientist. He's researched that. That didn't disprove anything he said. He addressed that. C, the ability of the liver to detoxify as manganese has been exaggerated. Well, that would actually help him because he's trying to get rid of it. His argument is, no, we don't need it. But he admits that, look, Inhaled manganese does not go through the blood to the liver. It travels directly to the brain. His problem is not that they're saying it's going to the liver and detoxifying everything. He's already addressed that. So it's not that one that's going to discredit him either. But if you look at D, it says inhaled manganese goes directly into the bloodstream. So his whole argument is that the inhaled manganese, when you inhale it, it goes directly to the brain instead of the liver. See, it travels directly from the nose into the brain via the olfactory nerve. So it would discredit him. That's the only one that's against him. And so that's why our answer is D. All right, number 4. Number 4, we're looking at a couple of experiments done on 2 different bacteria. There's a Y bacteria and an R bacteria. And all they're really doing is they're putting them in different substances, glucose, and amino acids, and looking at how they grow in those. Glucose is usually basically a sugar, amino acids basically a building block protein, and then the last one they do is they do them together. But the first experiment, they looked at just the R strain by itself in these things. Second experiment, just the Y strain in all of those. And the third one, they did both of them together, and they show you the growth results on here. So the experiment 3 was the only one where it's growing together. The question asks, under what circumstance do the Y bacteria produce a substance that prevents the growth of the R bacteria? Well, that means it's not going to be told by just the ones done alone. We're looking at when they're growing together. Does the Y one prevent the R one from growing, and usually helps itself? So we're going to look for dramatic change between what they did by themselves and when they were together. And if you just look right away, you can actually see one that stands out a little bit, but we'll look one at a time. So with F, it's when there is an adequate supply of glucose. Well, when there's an adequate supply of glucose by itself in the R strain, it grows very good. It grows poorly in the Y. When they're together, the R still does good, and the Y doesn't grow at all. So these were just small changes, but both of them were affected negatively. If both of them are affected negatively, the Y is not producing something to reduce the R growth, because it would only reduce the R growth in order for it to use up stuff. Since it's not growing at all in that's not going to be a problem. When the R bacteria are weakened because of a shortage of amino acids, well, the glucose basically is a shortage of the amino acids, and we didn't see really much of anything going on. H, when the Y bacteria has a plentiful supply of amino acids. So now it's saying, okay, does the Y affect the R when there's a lot of it? Well, when they're putting just amino acids, the R was poor, and the Y was didn't grow at all when they were alone, and they did the exact same thing when they were grown together. That means they're not reacting at all. They have the same results whether together or alone. So that one doesn't work. So hopefully it's this last one. When the Y bacteria have both glucose and amino acids available. So that's that last trial. And look at the dramatic difference. So when R strain is in just glucose and amino acid, it does really, really good. It does very good. But it did none when it was grown with the Y. The Y would only do good in that, but it did excellent when it was grown with the R one. So the R one is actually being hindered completely by the Y when they're in both glucose and amino acids. So when they're combined, it does something to where it makes something that would block the R from growing and benefit the Y to grow better. And so J is our correct answer there. And our last one is really talking about halogens. And if you've studied them, the halogen group and the reactivity of chemicals, it's a lot easier to do this one. But if you haven't, we can still figure it out. And so here's the general idea. It's saying that they have just the single elements, fluorine, chlorine, bromine, and iodine. Now, they're going to put those, with each of these experiments, they're going to put that chemical by itself in a solution of potassium salts of the other ones. So in experiment 1, they put chlorine with potassium chloride, so chloride is chlorine as well, potassium bromide, that's bromine, and potassium iodide, and then water is just like the control. Water means that you're just putting it in there to see what color it would show up if you just put it in there. And so the water will always show just the color of whatever was put into the solution, okay? So first they put chlorine, and it was green because chlorine is green in water. Iodine was dark brown because it's dark brown in that. Bromine is light brown in water, and so that's that. See? Now, it's not going to knock itself out of the compound. So when you put chlorine in with potassium chloride, it doesn't knock itself out. And when you put it in with bromide, bromide now is light brown, so it did knock bromide out. So chlorine knocked out bromide. And when they put it in potassium iodide, iodide's dark brown, so it did knock that iodide out of that dark brown. So we can see that chlorine knocked out both bromine and iodine. Now iodine, when they put it in, look at these colors. Dark brown, the color of iodine. So that means iodine never knocked any of them out. Bromine, however, when it was put in, it couldn't knock out chlorine. Light brown is what bromine looks like. It couldn't knock itself out. It's not going to knock itself out. It's what shows up in water, but it did knock out iodine because that dark brown is iodine. So we can say, wait a minute, then that means if I'm looking at reactivity, then I could say that the most reactive out of the ones they've done is chlorine. The next most reactive is bromine, because chlorine knocked two of them out, bromine knocked one of them out, and then iodine's the least because it knocked only one of them out. So you might go ahead and guess, if these are put in order, that fluorine would be more reactive than the rest of them, and it would knock out whatever it's put in. And so the question is, if fluorine were introduced into a solution of potassium chloride, what color would the water be? Well, if it's more reactive, it's going to knock out the chloride or the chlorine, and we're going to get green, that color green. And that is the right answer. It is green. However, if you didn't really understand reading all that, there's another way to do this. So you're looking at these and you say that the dominant one's going to join with the potassium and the non-dominant one is going to make the color in it. So you just need to know which is the most dominant and which is the least. Well, if you look at a periodic table, here's all your halogens. And in a column, your reactivity increases as you go up. So that means iodine is the least here, then bromine, then chlorine, then fluorine. And with fluorine, it being the most, it's going to knock out chlorine. Chlorine's green. And you have that the answer is G. All right. Hope that helps.